Hi everyone, I am Nakia. Welcome to another presentation. The title of this presentation is Binary Code, created by I am Nakia. Before moving forward, I would like to say the information I will be presenting, including future presentations, is a work divinely inspired, and I, Nakia, am verbally stating my intention to protect this information and the fundamental integrity of it from all misuse, intentional or not, public or private, in its entirety, with all rights reserved, without restriction. In addition, all information created and shared by me, Nakia, regarding this divine work is and will continue to be protected by forces that operate in truth and balance. All misuse will be recompensed with equal measure. Now, to keep the integrity of this information intact, what we know today as artificial intelligence or AI was not used to create or build on this information in any form. If and or when that time does come, it is of great importance to ensure the same integrity being used to carry out the duty of this information to the people is the same used to build a system of artificial intelligence or any other systems of knowledge. Keep in mind, programming isn't only what you see, it also includes what you don't see. And a lot of what we do not know in large part is because of what we do not see. Copyright disclaimer under Section 107 of the Copyright Act 1976. Allowance is made for fair use for purposes such as criticism, comment, news reporting, teaching, scholarship, and research. Fair use is a use permitted by copyright statute that might otherwise be infringing. Nonprofit, educational, or personal use tips the balance in favor of fair use. The origin of binary coding. The binary number system of modern day computing is credited to Gottfried Wilhelm Leibniz in the late 17th century. In his 1703 paper titled Explication de l'arithmétique binaire, he formalized a system using only 0 and 1 for arithmetic operations, showing how any decimal number could be represented in binary form. His work laid the mathematical foundation for digital logic. So here what I'm showing is that the binary system versions of it was used throughout history and in the past, right? So Mr. Leibniz is, like it read, is being credited for the modern day way of its use, right? So it shows here in ancient Egypt in circa 2400 BCE, the Horus I fractions used a form of binary to measure grains and liquids. And in China, it was the I Ching in the 3rd century BCE. They used hexagrams and trigrams arranged through binary progression for philosophical and religious purposes. It says here Leibniz himself studied this system. Pingala was used in circa 200 BCE in India, and they developed a binary-like system used short developed a binary-like system using short and long syllables to represent values similar to 0 and 1. And Thomas Harriot in the 1600s experimented with but did not binary arithmetic, but did not publish his findings. And then Francis Bacon in 1605 created the bilateral cipher, encoding letters using two symbols akin to binary digits. And so here on this slide, what I have here is what is known as binary numbers. And so when it comes to binary numbers, I am going to stay very surface level with this information. This presentation is just really about presenting information. And so here on the slide are binary numbers, and binary numbers themselves operate based on bits, right? And so, hold on for a second. So I just wanted to pull up an internet definition for a bit, and it says here, a bit is the smallest unit of data in a computer. Short for binary digit, a bit can hold only one of two values, a 0 or a 1. You can think of it like a light switch that is either off for 0 or on representing 1. So it looks like it says here bits are basically building blocks um, of all digital data. So be it text, photos, videos are made of millions of bits grouped together. So like I said, I'm going to stay on the surface with this. So again, I'm just presenting the information. What I want to focus on are these numbers over here to the right side. So here you have 1, 2, 4, 8, 7, 5, 1. Well, I'm reading it off based on this reduction, right? When reducing it to 1. So first, let me read it off for as it shows. So 1, 2, 4, 8, 16, 32, 64, and 128. And so when these numbers are reduced to single digit numbers, you end up with 1, 2, 4, 8, 7, 5, 1, and 2. And so throughout my presentations, I am introducing and talking about and making reference to numeric lines. And so there are two sets of numeric lines, two groupings. So what I call them, or I refer to them as the consecutive group and the non-consecutive group of 9 numbers, 9 numeric lines. And so with the non-consecutive grouping of 9 numbers, there when it comes to the 1 and the 8, the 2 and the 7, and the 4 and the 5, those numbers share the same numeric line. So, meaning 1 and 8 shares the same numeric line, 2 and 7 shares the same numeric line, and 4 and 5 shares the same numeric line. And so, I kind of want to make those numbers the focal point of this presentation. And so here, what I'm showing you are those same numbers, right? And so how do we get those numbers, right? How do we start at 1 and then get this string of numbers? So that's what this slide is showing. So 1 plus 1 equals 2, right? So that's why the 2 is here. 2 plus 2 is 4. So the 4 is there. And then 4 plus 4 is 8, right? And then 8 plus 8 equals 16. But when you reduce 16, it reduces to 7. So that's why the 7 is there. And then 7 plus 7 equals 14. And then 1 plus 4, when reduced, will be 5. And 5 plus 5 equals 10, but when reduced, will be 1. And so as you can see here, when you add it without the reductions, you end up with 2, 4, 8, 16, 14, and 10, and then back around to the 2, right, with the 1 plus 1. Because once you get the 1 here, it's going to cycle back around. It's just going to be on a repeat. So what you're seeing how is these string of numbers here, this numeric string of 6 numbers, these are repeated patterns. So it starts with 1 plus 1 to the 2, and then you take the 2 and 2 plus 2 equals 4, and then you take the 4, and then 4 plus 4 is 8, and then you take the 8 and you add that to itself, and so forth and so on, as you can see here. So what I'm showing here is how this pattern here is the same as this pattern here when it comes to binary numbers. 1 plus 1 is 2, 2 plus 2 is 4, 4 plus 4 is 8, 8 plus 8 is 16, but 7 when reduced, 7 plus 7 is 14, but 15, or 7 plus 7 is 14, and 1 plus 4 is 5 when reduced. So there's the 32 equals 5. And then 5 plus 5 is 10, but when reduced will be 1. But 6 plus 4 when reduced is also 1. And then 1 plus 1 is 2 again. So it's going to go on recycle on repeat. But instead of it showing as 1 like it's doing here up top, it's instead showing as 1, 2, 8. Because 1 plus 2 is 3. And 3, oh, apologies, this is the 2. The 6 and 4, that's the 1. So the 6 and 4, instead of it showing as 1 here, it's showing as 6 and 4 here, because 6 and 4 when reduced will be 1. And then the 1 to 8 is the 2. So 1 plus 2 is 3, and 3 plus 8 when reduced will be 2. So you can see here that, so even if this count continued, it's going to continue increasing in more than one number, but when it's reduced, it's going to reduce back down to one of these 6 numbers, 1, 2, 4, 8, 7, 5, and then back around to 1. So that's what I wanted to point out there. And then when you look at those numbers, so this slide here is just kind of looking at those numbers, those string of numbers a little bit more in detail, right? By separating it into parts. And so, because again, we're talking about the three, the six, and the nine. So, when you're dealing with the three, it's kind of like you're just dealing with the three. When it's six numbers, you're either, in order to balance that evenly, in order to explore it, you're either going to need to separate it based on two parts. So, three numbers for each part, or you're going to separate it into two parts. So you're going to six numbers. So I have it here. So you're either going to separate it into three parts to represent the two numbers in each part, or you're going to separate it into two parts for three numbers into each of those two parts. So hopefully that makes sense. Hopefully I did not confuse you there because that is not my goal. And so here I'm showing you here when those numbers are separated. So here I just kind of have them in order based on order, right? So meaning 1 plus 1 is 2, 2 plus 2 is 4, 4 plus 4 is 8, 8 plus 8 when reduced is 7, 7 when reduced will be 5, and then it cycles back around to the 1. So here I kind of separated it into three parts for the six numbers. So here you can see when 1 plus 2 is added is 3, when 4 and 8 is added is 3, and when 7 and 5 is added is 3. And then the same 2 and 4 when added is 6, 8 and 7 will be 6, and 5 and 1 will be 6. And then 4 and 8, 3, 7, 5, 3, 1 and 2 and 3. So as you can see here, as through that process, you can see how those patterns produce the 369 pattern. So 36, 36, 36. And then here down at the bottom, I'm separating it into two parts for those six numbers in order to explore it based on balance, right? So here this grouping is the 1, 2, 4, and when these three numbers are added, it equals 7. And then this 8, 7, and 5, when added and reduced, will be 2. And 2, 4, 8, when added, is 5, and or will be reduced to 5. And 7, 5, and 1, when added and reduced, will be 4. And so, as you can see here, these groupings of numbers, when reduced, adds up to 9. So here, this pattern and this sequence of numbers is basically repeating in and of itself the 369 pattern. So here is the 3, 6 up here, and then here is the 9 down here. However, even this 3, 6 up here, when added together, is 9, right? So here, what I'm showing is the Eye of Horus, as I read off of that slide up top. The Eye of Horus fractions is a set of sacred unit fractions attributed to the ancient Egyptians, representing different parts of the Eye of Horus. And so if you look at the Eye of Horus, you can see here those numbers, right? So I'm looking at the bottom numbers here. So right here, it would start at 1, right? Or even 2. It doesn't matter where it starts because it's going to cycle back around throughout those same numbers. So here would be, I'll start with the 2. So here's the 2, and 2 plus 2 is 4. 4 plus 4 is 8. 8 plus 8 is 16. All right, but 16 when reduced will be 7, and then 7 plus 7 is 14, 5. So 3 and 2 is 5, and then 5 plus 5 equals 10, but when reduced will be 1. And 6 plus 4 when reduced will be 1. So you can see here that sequence of six numbers. And um, so what's that showing you? So what does that mean? That means that this information is not brand new information, right? It means that this information has been out there for quite some time, is what this all means. And so here, what I have here is I have the Eye of Horus, and then I have the eight-pointed star, right? And so what I wanted to know is if the eight-pointed star is the inspiration for the Eye of Horus. And so what I'm going to do is I'm going to attempt to use this drawing tool here to kind of draw out how I see it, or where I can see a definitive yes when it comes to questioning whether or not the eight-pointed star was used as the inspiration for the Eye of Horus. So here would be the brow, right? That 1/8. And so this would be the brow right here. And then the 1/4 would be the eye. So the I would be pretty obvious, right? Right here. And then this part right here underneath the I kind of going into that half, that would be this right here. So this would be kind of going up right here. So this part right here, it would be this line right here, and then it would kind of, I guess, go out like down maybe like that a little bit. And then this part right here, it would just basically kind of continue up and then down or maybe out. Hold on for a second. Okay, apologies. I needed to erase and start over. So, okay, so back starting with the brow. So the brow would be here, this area there, and then the eye, and then this part right here. Let me see, let me get it. Okay, so the brow would go further out like that, like that. It's not perfect, right? And then this part right here would be this part right here, right? It would go down and then go in right there for both sides, down. And then this part looks like it goes down right here, right? And it would go right there. So hopefully you're seeing what I'm seeing. It's not perfect. Um, and then this part would go down. So here would be this part right here. So it would go down and then it would go out right here for this part right here. And then this part right here is right here, right? So going up and then going out and then going down right there. Well, it would go down right there, right? And then this part right here would be, it would be this part right here going down like that. And then this part would be this part going down right here like that. And then this part right here would be this part going down like here and then going back up. So it's not perfect, but the point that I'm trying to make is that the eight-pointed star it can be definitively said that the eight-pointed star was the blueprint, the inspiration for what we know to be the Eye of Horus. Okay, so what I want to do now, so here on this slide, what I want to do is I want to show, I want to continue with the eight-pointed star being the inspiration. So here I'm showing where the eight-pointed star being the inspiration and or the blueprint for what we know to be the number 10, right? So okay, so here on the left side, so here up top, you see 124875. And then here is the 9 numeric grid. So this will be the 1, 2, 3 vertical, right? And then this side will be the 1, 2, 3 vertical, but it's mirror opposite, right? So here on this side, this image right here will be based on this numeric grid, and this image here will be based on this numeric grid here. And so this is what basically is drawn out when this numeric string is drawn out on this numeric grid. So one would be right here. So one would start right here. So when that's drawn out, you would draw the 1, 2, the 2. So the 1 would be here, the 2 would be here, and the 3 would be here. So it would be 1, 2, 3, 4, 5, 6, 7, 8, 8, and 9. And so the 1 starting with here, you would draw the 1 to the 2, and then up to the 4, and then over and down to the 8, up to the 7, and down to the 5, and back up to the 1 since it's cycling, right? Or repeating and or repeating. And then 369 would be right here. So 369 is here, so it would just be a straight line. So 369 would be right here, a straight line. And so this little graph that I have here is just to show the 0 and the 1. So this would be the 0 and this line right here would be the 1. And so the same logic applies for the image that you see there on the left. So the 963 or the 369 would be on the top right here. And then the six numbers that make up this image here would be at towards the bottom. So starting again with the one, so the one would be here, one, and then two, and then three. So starting at one, down to two, or up to two rather, and then uh, one, two, hold on for a second. For some reason, I wanted to jump to eight before going to the four. So starting over, starting here at the one, so one to two to four, and then to eight, and then seven, and then here to five, and then back up to one. And so as you can see here, it's the same image for both sides. The positions would be the only thing that's changing. So here in this graph I'm showing here, you hear how the one, this line here would be the representation as the number one, and this image here would be the representation as 0. And then here on this slide, same image, same process. So what you're seeing here is based on the 1, 2, 3 horizontal for each side. So 1, 2, 3 horizontal for this image here, where the 0 and the 1 is here. So this would be the 0 and this would be the 1. And for this one, the 1, 2, 3 is at the bottom. So the the mirror opposite of the 1, 2, 3 on this side. So the 1, 2, 3 is at the bottom here. So the 1 is here, 1 and 1. And then this image here would be a representation as the number 0. So again, what I'm showing you here is how the 8-pointed star, based on this numeric string here, the 1, 2, 4, 8, 7, 5, and with the 369 being separated from those six, but basically it includes all 9 numbers. What I'm showing you here is that the 8-pointed star was the, or is the inspiration for what we know to be the number 10. This process is a process that allowed um, the ability in print to be able to show numbers in, but going from a single digit to 2 digits, right? Beginning with 10. And it all started with the 8-pointed star. And so here I'm showing you what it looks like when all 4 of those sides come together. So you see here, it can appear to look like many images. And so it all depends on perspective. And so one perspective that we all are probably familiar with is this perspective here, right? So this is like the checkerboard floor. When you see this image, you can see many things can come to mind, like the checkerboard floor that we see in a lot of movies and in homes. This represents duality, a chessboard, a checkerboard. Um, there are many representations of the image that you see here. And so now you know that this image that you see here is based on this string of numbers 1, 2, 4, 8, 7, 5, and to include the 3, 6, and the 9. And then here, this image, these two images here would be based on that 8 grid, right? So excluding the 9. So here, so if you notice here, there are no 9s. And the reason why I only have the 2 here is because when it comes to these two sides, you only need one of each side in order to bring together a complete image. And so here, the 864 as my point of reference is at the vertical. And well, wait, hold on. Maybe I'm misspeaking again. Let me look at what I got here. Okay, yeah. So it looked like I do have both sides. I apologize. So here the 864 here is at the vertical here and is at the vertical here. And so when this numeric string is drawn out based on these grids, the image that you see here is what is able to be drawn out. So using this one here, for example, the one would be here. So starting the line here, you go from 1 and then up and over to, or up to 2, and then down to 4, and then up to 8, and then down to 7, and then up to 5, and then back down to 1. So that would be the same for both sides. And then here would be the other two sides, so 4 altogether. So again, the point of reference will be the 864. And so the 864 you see here is at the horizontal position for both sides. And so the 864 on this side is left to right, and on this side is at the bottom from right to left. And so it's opposite. And so here you can see here an exact image or duplicate for each side. Same here, each side. And so when these two image or those 4 sides or two sides come together, so 2 and or 4, because again, these two sides are the same and these two sides are the same. So when when you take one of each side and you bring it together, it will create the image that you see here. So this, once again, it can be seen as another version of the 8-pointed star. So the points would be 1, 2, 3, 4, 5, 6, 7, and 8. And so this video, my goal was to make this video short here. I just kind of wanted to, like I said, just kind of, but the focus would be, I just wanted to present the binary numbers and show the origin of the numbers and show how the 8-pointed star is the inspiration for what we know to be the binary system and or the number 10. And so I think I have done that. Um, if you have any questions or comments, please leave them in the comment section. Thank you for watching. If you enjoyed, please like, share, and subscribe, and I will meet with you in the next video. Bye.